So thank you, Jarno, for coming to us to talk today. Over to you.
All right, thanks. Finally, we can talk a bit about GPUs. So this is the first part of a two-part series with me and Michele again. And that means that I will not get into some topics. I will not talk about coding, and I will not talk about different languages. I will mention a bit about optimization, but not going into much details. This is much more of an introduction and background, what the devices are like, essentially. Okay. Of course, we can get into anything without much presentation. So just a bit of background, essentially. So we're talking about graphical processing units, or GPUs, or general computing on graphical processing units, such as GPU, you see that acronym also around. The origin of the thing is, of course, in two-dimensional graphics processing, so specifically purpose-built devices to process graphics to show on a two-dimensional screen with, in the beginning, rather limited amount of pixels. And the point was that already at that point that you essentially operate on 1 pixel at a time, or at least sort of produce 1 pixel at a time, maybe taking data from the surrounding pixels, but not the output. And of course, you also have the coordinates coming in. So the inputs are essentially they have the coordinate, and there's some information about the pixel that you are supposed to render. The inputs stream directly on the device, which is on the way somewhere between your screen and your machine and your motherboard. They get transformed in some way, and then they are pushed directly onto the screen. This is the background where essentially all the limitations come from, and all the performance. Okay, so in the 90s we started seeing some 3D graphics, and it essentially started with rasterization. So you could do rasterization on the chip rather than, or on the GPU rather than on the CPU side. Right? Rasterization means that you have 3D content, and in this context it's worded with a lot of meanings, but in this context it means that you have some 3D content that's built out of simplices, essentially triangles and points. And you project those points and those lines from a 3D picture to a 2D surface. Yes, the best picture I could get without any copyright problems from Wikipedia. So this is actually more looking like a 2D going to 1D, but that's essentially fine. So there's a 3D view or objects in a three-dimensional space, and you decide that the viewer is in some specific place of the screen, essentially shows one specific cross-section, and then you project from that. The view and the viewing angle are essentially independent variables. Okay. Then we come to shaders in around 2000s, which start to get more programmable. Things start to get more complicated. So you can the design. The point of this is to produce the surface texture of an object on the GPU side. And this was actually possible in the openCL library directly already way before, but it's started to be supported by devices around 2000s, Nvidia getting into this. So these are not extremely programmable at first, of course. Some predefined functions, and the point was that you can produce lighting and you can produce texture on the fly using essentially the same kinds of processing or cost-saving strategies that you use for the pixel and the pixel processing and the rasterization. This is essentially the same concept. You have a lot of independent data that needs to be processed in the same way. Okay. There's also vertex shaders, which is essentially means shaders that take the three-dimensional picture with the synthesis and somehow transforms it, either moves it around to create some effects or creates new vertices. So you might take a crude looking ball, so with a relatively small number of triangles, and add some on the fly and then rasterize that on the screen. So here's a basic example. So you can you see it? Well, I mean, this also this is supposed to show the what the simplicities look like in a three-dimensional thing. This is a ball, of course, and this has been built out of squares. So every simplex has 4 points. Now, the one on the left has been shaded just to show the flat surfaces better. So all these surfaces are shaded as if there was a point of light here, and as if there were flat things on the wall. But where it, of course, becomes much more useful is that you can do shading something like that. So it still has exactly the same vertices, except it has the same flat surfaces, but they are shaded as if they were round. This is you can probably imagine this is a relatively straightforward operation. It's a transformation with some cosines or some polynomials. You have to take into account the direction of the light source and the direction of the viewer, and essentially just first you produce pixels on the three-dimensional surface, or the lighting on the three-dimensional surface. Then you project that, you recalculate the lighting and the texture of the pixels, and then you put that on the two-dimensional screen. Okay. It's another example which shows even more badly. This is unfortunate. Can't really make it any more bright. This is supposed to be a smooth sphere, and this is just an example of a transformation that you can run on a GPU. So here's a map of bumps, and you map them on this sphere, so this becomes a shadow here, and all the smaller ones become shadow there on the surface. So it looks bumpy like an orange. This doesn't change the three-dimensional structure of the object, so if you render a shadow, it will be perfectly round, but it changes the way the surface is rendered on the screen. So again, this is a transformation that you do pixel by pixel. Actually, this is a pretty straightforward example, because every pixel here maps onto one pixel here and changes the lighting, changes the dark light of that particular pixel on screen. Okay. But it also, it does a transformation that maps it onto the surface of the sphere. So the point is that these are all very simple programs, relatively simple mathematics. They take in a relatively small amount of data, and they produce data independently of all the neighbors. And they might read in the neighbors, but they don't need the output of the neighbors. And they all perform exactly the same operation on all the points at once, for a very large number of points. They are vertex shaders, essentially, and if they take one vertex in, they do a transformation, and they output the position of that vertex. Or maybe they take a couple of pixel shaders. Of course, they take a pixel in from multiple pixels surrounding each other. They do a transformation and they produce a pixel. Geometry modification, tessellation, especially. That tessellation is what I said. You take one of those simplices and you add some more. You essentially decompose that, following some geometric description into more smaller surfaces. That takes in a small number of vertices and produces a small number of vertices. Now, this was just NVIDIA's first came out with a essentially programmable version of the shader, so you have the ability to write functions that are run on pixels and use whatever effects you want. There were some examples of this in Wikipedia, but it was essentially just this sort of image maps where you just randomly change the colors. So, okay. But you can imagine that you can essentially change the internals if you want to do some special graphics. Something that the device manufacturer didn't think about. Okay. Now, at first you would have to translate all of these into graphics primitives into a description of graphics that is supposed to be then output to the screen. But of course you can, instead of outputting it to the screen, you can output it back onto your computer. You can interpret the output of the device in any way you want. So if you can translate your problem into the correct graphics primitives and run some functions either on the vertices, there are some more vertices, or changing the pixels, shading of the pixels in some way, you can run some computation. And if the computation fits into the idea, the original idea of how this hardware was optimized, you will get a relatively good result compared to a standard CPU. So the first thing, the matrix operations are relatively straightforward because essentially what these 3D transformations, graphics transformations are matrix operations. So they're relatively straightforward to translate this way. So the first thing that actually ran faster than on a CPU was an LU decomposition program, large matrix. And since then, well, there have been programming languages designed for general purpose computation, like CUDA and openCL. Now there's OpenMP library and OpenACC.
Good question. I guess the LU decomposition is still there has to be a largest matrix for which it will be faster on the GPU than the CPU.
Yeah, and the smallest.
And the smallest. So it's a mid-range on a mid-range matrix.
Yeah,
it is faster on the GPU.
It was faster in some specific size, some specific situation.
Yeah. And
the amount of problems where a GPU is faster than a CPU is growing. Because these devices are being optimized now also for computing use. You have separately graphics devices and computing-oriented graphics devices. And secondly, partly because of the building of these general-purpose languages to translate things in ways that are easier to deal with. So you can just write essentially normal C code in CUDA or C++ code in CUDA and get something out that you understand. You don't need to learn anything special. openCL and OpenACC and the new OpenMP implementation are straightforward in CUDA. Although CUDA is also evolving, of course. I don't want to give the impression that CUDA is somehow getting behind, it's also evolving. It's just like
it's a very considerable upgrade compared to what they were achieving in terms of these parallel matrices, true blast, true sparse. In the past 5 years, they have achieved so much in terms of speed up they were trying.
Yeah. And nowadays you have specialized hardware as well. Okay. So we have said most of this already, but just to reiterate, so the reason that you use a GPU and the reason that GPUs are faster in some cases is that they are specially built for solving specific kinds of problems. And these are similar to rendering graphics on screen. So in a device you have a large number of cores that perform the same operation on large number of data, which essentially means that you assume data independence. You assume that the next pixel doesn't depend on the transformation of the pixel on the right, only the original value, not the transform value. Okay. So you can do all the operations at the same time on separate small cores, and you have essentially no branching in the kernels. Branching is pretty bad. And you have a limited control, limited number of operations, limited control meaning program flow control, instead of like for loops. Okay. This is sort of a map of what the GPU would look like. So there's a host device, which is the CPU, and it has some internal memory, some cache. There is a device, and the host and device memory is controlled. They communicate through a DMA interface. There is a thread execution control unit, so a control unit, which sends operations to the execution units to be performed. But in this diagram there's just one, right? It just sends one command to everyone. It can send different commands to the different units here, but every one of them has a number of cores that always do the same operation at the same time on the data that they happen to be looking at. There's a better map of the Fermi series a bit later, so I won't go too much into it. These do all have their own sort of small cache, register memory, and some special execution units. But okay. So then you have large SIMD units. You have comparably low memory bandwidth even inside the chip, and especially the transferring between the CPU, of course, and the device. This comes sort of from, if you imagine, from sending data through the device on the screen. The latency comes from sending it to the screen, not sending it to the device. In this case, there is latency from sending it to the device and sending it back compared to just the decomposition, of course, because it's not on the CPU, or at least it's as close as the computer is on the CPU. Okay. There is a limited amount of memory, at least you get a small amount of data, you do a predefined transformation, you push it out. Now, recent models do have native double precision, and they do have multi-level caches. So some of the programmability problems of the original devices that maybe some people started doing computations with 5 years ago, some of those problems are alleviated with the newer models, especially the ones designed for computation. The V100, which we will have no, this is the better picture of this is from the Nvidia's Fermi compute architecture white paper, which I found on Wikimedia. Unfortunately, I didn't find, or I'm not sure if the newest model had the same kind of picture, but you can look for just the Tesla V100, the Volta white paper, because that's the one we have on the Sunbird. So it's pretty similar, and I can tell you what the differences are. This is a single compute unit. It has an instruction cache, of course. The instruction cache is shared between all the execution units. And it has schedulers, these Bob schedulers. They schedule essentially instructions to a Bob, which I believe is half of this unit. That's 16 cores. And dispatch units. They have a shared register file from which they essentially all the compute units read at once from the register, so as if they are capable of reading sequential memory. So, well, I will come back to that. And then you have compute cores. This is from Fermi, so you just have one kind of compute core, but actually on the Volta you have a single precision core. You have 64 single precision cores and 32 double precision cores. So they operate on the same amount of memory at a time, but the double precision cores are this half the number. Okay. Then you have separately load and store units, which are now, of course, capable of loading and storing from the shared memory exactly the same number of floats, well, actually half the number of floats as you have floats. or half the number of doubles of cores. So they read one cache line at a time. And then you have some special function units that can execute some more complicated functions. And then there's sort of the whole device memory and the device cache and the connector journey as well. So the Volta 100, which we will have on Sunbird, has 80 of these streaming microprocessors, which are essentially very much like this, except each one has an output 32 double precision cores per streaming microprocessor, and 64 single precision cores. They have 250 kilobytes of register file, which means that there's 8 kilobytes per core. You have to keep that in mind when you're writing your kernels, because if you use more than that, of course, you will have some scrolls, you will have extra loads, and that costs a lot of time. Okay? You have level 2 cache, which will reduce the problems of cache space. And then you have 8 tensor cores, which are important if you're doing machine learning. If you're doing machine learning, you might have use for them. They're essentially designed to execute these fused multiply add operations in half precision, so that they multiply in half precision and add in full precision to do quick matrix multiplication and add operations. So that's all you do in machine learning, essentially. If you were here in program machine learning, that's all there is. So, it's okay. Just one as I said already. Okay. So, things that you need to take into account when you're actually thinking if your application might be, if you might try and write that to support GPUs or to GPUs on the server. The most important thing probably is still moving data to and from the device takes a lot of time. It's usually best to keep everything on the device, at least in the projects I've been involved in, which are mostly you keep all the data on the device at all times, and sometimes you make some deductions and then move that to the CPU to bring on the screen. But that's actually all asynchronous, so the simulation keeps running on the device. The CPU is needed though to give instructions to the device all the time. But cache loads and writes are also expensive, a lot less expensive, but in terms of probably hundreds of cycles, like hundreds of thousands of instructions, so because you of course have a lot of instructions per cycle. The devices try their best to hide the latency. So they try to run your kernels while loading data for the next kernel. So you want to sort of have heavy kernels. You want to do a lot of compute operations on each run, on each cycle. Cycle not meaning compute cycle, cycle meaning cycle of I load the instructions, I load the data, I run the kernel, I get to store the data, and I'm done. Right? You want that load and store to be a relatively small part of the whole thing, which is very hard because the device can do a lot of computation. Okay, and when you think about that, you need to keep them small enough to avoid spills. So avoid using more memory than you have in the registers, especially more than you have in the cache. And then, of course, the basic thing, you have to be able to write your program so that every core always does the same instruction. So you need to be able to write your program in a way where there's a lot of independent operations running at the same time. But if you have a problem that fits that description, it will probably be faster than GPUs. Okay, and you need to avoid branches inside the kernels. inside the single compute units. Because then it will essentially do the whole thing. If we have one if statement there, it will do the whole thing. Okay. Now, it's probably something you see in any lecture or interaction that you do on this picture. So the load store units that you have added at lecture on the picture, they can essentially do a single load of a full cache line at once, which means they can load one single precision number for every compute core at once, as long as they are stored consecutively in memory. So, and if they are from one cache line, of course. So if this is one cache line, you can load the whole thing at once in such a way that the first compute unit can use the first one, the second can use the second one, the third can use the third one, and so on. Even if you are not actually quite aligned with the cache line, if you start from here, it's only two operations. But if you do strided reads, right? If your first core tries to read the first one, the second core tries to read something 8 bits here, or 8 bytes here, and the next one tries to go 8 bytes here and so on, that's a huge number of memory operations. And they all come to separate memory operations, they don't get aggregated. Okay? So that's what you really need to avoid that and try to put all the data consecutively in memory. Preferably aligned to cache lines. This is, I said that this is one float per core. This is also actually one double precision number for a double precision unit because there's half the number of double precision units. Okay. Alright. So this is more or less the point I made a bit earlier. If you are thinking of if it's worth actually using GPUs for your application, these are the things you need to think about. You need to have a lot of computation compared to data, compared to memory bandwidth. You need to have large matrix operations, or you run consecutive lines of data that need the same operation applied to them, and you need to store them sequentially, right? And you don't want to communicate with the CPU too much. That's more or less what I have. Yeah, so there's other accelerators out there that are sort of evolving as we speak, and might be useful in your cases. We will not have any of these on the cluster, but might be worth considering for some applications. FPGAs are basically more programmable, more customizable, but they are essentially you can take one and reprogram it to be a purpose-built device for your particular program. But it requires that reprogramming, which takes a good amount of time, and requires that you can write a program for it, which is not necessarily as straightforward as using OpenACC or OpenCL. Then there are these Tensor Processing Units emerging. This probably become a lot better in the next few years. Right now, the only one really commercially in use that I know of is Google's Tensor Processing Units, which are not for sale. They just use them themselves. But I have seen sort of noise about a couple of companies making specifically purpose-built devices for artificial intelligence. So this would be this would be somewhat different from GPUs. It would probably have more tensor units, probably be faster in doing the pure multiply add operations. And maybe the data structure would be something